So I just copy and pasted the table that we put together. I'm anticipating an answer around 280 pounds of salt when the tank overflows. Now, I'm going to plot. So what I actually have is a numeric solution, right? A numeric solution. It's not pretty. It's a table of values, but it's there. And by the way, that's how you solve differential equations numerically. You just or kind of how you solve them. This just won't be, the time steps will be much smaller. All right, so I'm going to plot the time in hours. So every 10, time step is 10. And then I'm going to plot the salt in the tank in pounds. All right, so I am going to solve this in closed form. So I know my final answer is going to be, I'm anticipating something around 280 pounds, or that order of magnitude at least. So the question is, what kind of a function do I expect? Well, what does this look like? So this function looks like, well, if you pay attention to the dots, it kind of looks like a wave, which makes sense because the amount of salt being added is a cosine function. So it looks like a wave, but also a wave that's increasing, almost like a line. So maybe we're anticipating something where it's a linear function of some sort, a combination of linear functions and wave functions. All right, so we have our common sense check set up. We're anticipating an answer of 280 pounds. The function has to be a wave function and a linear function. All right, let's try to solve this thing. Oh, okay, before we solve it, we have to actually write the differential equation. We have to do the thing that a computer cannot do. All right, so let's set up some variables. T is the time in hours. Q of t is, okay, again, you can solve this by making Q of t the pounds per gallon. But I'm going to make Q of t amount of salt, just pounds, in the tank at time t. All right, so we don't know how much salt is there for each hour, but we know how the amount of salt changes, and that's kind of what a differential equation is. So change in amount of salt, pounds, in the tank equals, this is how much, right? We're just studying the change, so we don't really need to know how much is in there like we did for our table. So how much is coming in? It's 9 gallons times 1/5 plus 1 cosine of t. And then how much is leaving? All right, before we figure out how much is leaving, let's do something you probably did in science class. Let's do a unit check here. Change amount of salt is pounds per hours. So 9 is gallons per hours. This expression is pounds per gallon. So the gallons cancel out. We have pounds per hour. Whatever we're subtracting here, whatever amount is leaving has to be pounds per hour too. So what's leaving? 6 times however much salt is in the tank at the same time. And you might say, well, I don't know how much salt is in the tank at the same at a time t. Right, that's what we're trying to solve for. That's what we're trying to solve for. So, right, a differential equation, you don't know what the process is, but you know how the process changes. You can measure how something changes, not what it is. But, okay, so Q of t divided by how much, right, Q of t is the pounds of salt at time t divided by gallons at the tank. So it's 600 plus 9t minus 60. So this is going to be gallons per hour times pounds per gallon. So the gallons cancel. All right, the units match up. You didn't let pounds equal to hours or something crazy like that. All right, so let's change this to algebra. So you have Q prime of t equals 9 times 1/5 plus 1 cosine of t minus 6 times Q of t divided by 600 plus 3t. And the initial condition is Q of 0 is 5. All right, I'm going to simplify this further. And then the 6 and these, so right, it reduces. You can pull out a 3. And I'm going to write this as 9/5. All right, so you're looking at this. Do you recognize this as an ODE you can solve? Well, yeah, it's a linear equation. It's a linear equation. So help us God, because this is, right, a linear equation where neither P of t nor Q of t is a constant. All right, so let's try to solve this linear equation. You can pause here and see if you can solve it on your own. The answer is going to be crazy. All right, so here we go. I'm going to solve this linear equation. Here it is. Do you remember the steps of solving a linear equation? Step number 1, write it in the correct form, right? dy dt plus p of ty, g of t. So what I'm going to do is I'm going to swing this term to the other side. And I should have written this 2 over 200 plus t, but still, okay, swing it, okay. And then we're going to introduce this concept, the integrating factor. Mu of t equals e raised to this. The p of t is 2 divided by 200 plus t. So you have e raised to 2 times, right? The integral of 2 divided by 200 plus t is the natural log of 200 plus t. T is positive, that's why we're not going to put absolute values on here because t is time. So 2 times that, and then you apply the properties of logs. You square the input and then the inverse properties of exponentials and logs. You get 200 plus t squared. Okay, so step 3. Do you remember that step? You multiply everybody by 200 plus t quantity squared. The left-hand side becomes the product rule, so you can write it as a product of 200 plus t squared and q of t. And this is just what you had on the right, 9/5 plus 1 cosine of t times 200 plus t squared, and you integrate each side. I'm going to skip the steps for this integration, so if you want to pause here and do it to see if you can do it, the way you would integrate it is to use tabular integration by parts, or you can use integration by parts 3 times. Let u be this function, 200 plus t squared. It's a polynomial. Its derivative will eventually be 0. And let dv be 1 plus cosine of t. It's going to have integrals. Its integrals will never die, but they'll be easy to find. And I'm going to leave that part out just so the slide doesn't get too crazy. You can pause here. I'm going to integrate. Okay. If you integrate, so on the left you just have the product. If you integrate, you distribute and then reshuffle, recombine, reassemble like terms, you get something like this. Remember the c we add once. You need the c, by the way, because otherwise you're not going to be able to get to a particular solution. You can add it here, you can add it on the left side, or you can add it here. The convention is just to add it on the right side before the final step. All right, so here we go. And then step 5. So here's my, step 5 is to solve for q of t. So here's my function. I mean, it's not pretty, but it's a closed form function. No crazy, right? All functions are algebra 2 trig functions. Okay. And then apply initial condition. 5 equals q of 0. I mean, are we getting a break here? Nope. C is negative 4,600,720. Okay, so here's our particular solution. All right, now comes the moment of truth. If I plug in 300 for t, will I get an answer near, what was it, 280 pounds? All right, let's do this. I'm going to plug in 300 for t, and I get 279.797 pounds. All right, you can actually graph, I graphed this function on Desmos, and it does look like it fits. It does look like it fits our data. It does look like oh, by the way, we did get what we anticipated, right? We said it was going to be some sort of combination of linears and trig functions. So there it is. All right. Okay, mixture problems. Calc 4 Classic. Okay. Just going to look at one more problem, a population problem, and then next lecture we're going to look at more population problems, but this one is